No questions? All right, so let's go back to talking about networking. So you know about IP addresses, right?
Mm-hmm.
So 192.168.2.3 or whatever, right? 4-part address. And what do IP addresses refer to? What are they the address of, typically?
A server or a computer?
A computer, right? Or a server that's a computer. It's a machine usually, right? Virtual or physical. But it could also be, you know, your smartwatch. It could be your microwave oven. The Linux server has an IP address. ctech.clark.edu has an IP address. And how many people are comfortable with the idea of like Internet versus Intranet? The whole idea of a router and setting up your own.
What's the difference between intranet and internet?
So inter is like international, between nations. Intra is within. International would be within one nation. So an intranet is usually inside, say, a business or a building or an organization. An internet connects all these different places together. But usually you're not connecting one machine at Clark to one machine at Intel to one machine at WSU, right? Usually at each of those sites there's a whole collection of machines. And if you've got 2,000 machines sitting here at Clark, you don't really want to take up 2,000 addresses on the internet, right? So this 4-part address, each of those things goes from 0 to 255. It's 8 bits. So your entire address is 32 bits. That's 4 billion possible addresses if you used every single combination. A lot of combinations don't get used. When the network started, that first number was either 10 or 26. 10 was called ARPANET, and that was what schools and universities were using and researchers to develop networking. 26 was MILNET. That was where all of DoD and other government agencies were putting their computers, and that was it. You had either one of those two addresses in the front, and if you stumbled onto MILNET, it was always interesting. So it was never intended that you would have 4 billion devices connected together, right? We've far surpassed 4 billion at this point, right? Which is why years ago they were talking about running out of address space. It could only support 4 billion unique addresses. And some of that is mitigated by the fact that all of the machines here at Clark take up just a small number of addresses on the internet, right? So we have a local intranet, which is a collection of routers, and every device here at Clark has its own address if you look at the address in our local network, but they all communicate with the outside world through possibly one router with one IP address. And anybody on the outside world who wants to talk to my laptop or your microwave oven or your smartphone is doing it through this one machine on the internet that Clark has, and it gets all those connections and it routes them to whatever device those are destined for. So you have these local networks and they're connected together through the internet. We still ran out of address space. So now we use 6-bit, 6-piece addresses, larger space. I sat in a talk a few years ago at Virginia Tech by a guy named Vint Cerf. He was one of the creators of all of this network stuff a long time ago. And he and some friends were coming up with the addressing scheme, and some of them wanted to do 32 bits and some of them wanted to make it bigger. And he convinced them to go with 32 because it was easier. And he said, if this actually works and it catches on, we'll make it bigger later. And it was like decades before they ever got around to, people got around to reworking that. So he's like, that's my bad. So an IP address gets you to a machine. There's also something called a port number. And this is typically something from 0 to 65, 535, a 16-bit entry. That's good. And the combination of IP address and port number gets you to a particular piece of software, usually running on a particular machine. So IP address gets you to a machine or a host, and port number gets you to something running on that machine. And the things we're going to use to do this communication through ports is called a socket. And sockets are, you can think of them kind of like virtual files that can be shared by two entities. So I can open a socket, you can open a socket, they can get connected, and whatever I write into my socket, you can read from yours. Whatever you write into yours, I can read from mine. So it sets up a communication pathway. But you name a socket with an IP address and a port number, which means it doesn't have to be on the same machine. It could be on a different machine, could be on a totally different, part of the planet. And so you're trying to send information back and forth. Okay, so for PA5, you're going to have something for sending messages between a client and a server, two ends of a chat program. And you can set that up more or less however you want, right? If you want to send the name of the person who's chatting with you, you can say, okay, the first line you get is going to have the person's name. And if you get a message that starts with this, that means the connection is shutting down. You can set up whatever protocols you want. But when you're trying to make a communication network that's going to work across the entire planet, right, plus space station, and have longevity, you got to have some kind of reasonable standard for what you're going to send and what it's going to mean. So there's a series of protocols. One is called the Transmission Control Protocol, which is TCP. The other is the Internet Protocol, which is IP. And those are two specifications for how to take information and bundle it up and send it to somebody. And they're part of a larger hierarchy. Which we can think of as either a 4-layer or a 7-layer stack. So if you think of this as 7 layers, it's basically a breaking down of function from highest level function, which is the application layer. So this is your web browser, this is your PuTTY client, this is your music player, right? It's the high level stuff, all the way down to the physical layer on the bottom, which is the thing that's actually controlling the voltages, or the electromagnetic radiation, or the infrared signaling, or the sounds across the telephone line. The thing that's actually sending the ones and zeros, right, in some physical medium. And this is layered because, we used to use wired connections. You plug your cable into the side and you plug it into the wall and you're tethered, right? And more people started using wireless connections. Well, to switch from a wired connection to a wireless connection, you don't need a new browser. You don't need to download or update your browser. You don't need to recompile your code, right? The same browser, the same application works regardless of what the physical medium is, right? That's what's guaranteed by having this layered hierarchical model. Now, something has to deal with the fact that we used to go through a wire and send voltages, and now we're generating electromagnetic waves and picking up signals and interpreting them, right? That's happening down here at the physical layer, at the data link layer. But the application layer only cares about, in TCP/IP model, only cares about the transport layer. This TCP, Transport Control Protocol. And TCP doesn't care about the network layer, it just cares about sending things at this internet layer. The internet layer is going to worry about the physical networking. So early 80s, DARPA, Defense Advanced Research Projects Agency. I can't zoom in. That's okay. It's just pretty to look at. DARPA prepared this RFC, request for comments, on the transmission control protocol. This was a published document basically to let people look at this and talk about it and make suggestions on it to help build this internet, right? And so RFC 793, every RFC had its own number associated with it. This was the TCP RFC. And it's all, you know, good old ASCII. So you've got ASCII art, right? Nice picture of the 4 layers. Right, and so application layer Telnet, that's the insecure version of SSH. FTP, that's the insecure version of SFTP. Voice, which never really caught on too much. So web browsers, games, all that sort of stuff. And if you go down a little further, you find this wonderful diagram. This is what a TCP header looks like. So every time you want to send data using TCP/IP, you make a header that looks like this, and it starts off with 16 bits specifying the port that this is coming from, right? It identifies the unique socket on your local machine, and then 16 bits specifying the destination port, where you're going to. Going across multiple links from one machine to another, there's different paths you can take. I might send a link from here to there, and it goes through one machine in between, and that machine might start running slow because someone's downloading something, and so my future traffic might get routed through some other machine that's further away, but faster or less burdened. And the stuff that I send, packet 1, packet 2, packet 3, might show up as packet 3, packet 1, packet 2, right? Out of order. So there's sequence numbers in here so that you can put these things back together, right? All these things that you have to sort of take into account, because you're no longer just working on your machine with your nicely controlled environment that you built. You're working with any machine that's out there that's conforming to a certain set of standards that can be part of the communication. So there's a checksum, right? 16 bits to help you know if any bits got flipped, and some flags and other stuff, and then way down here at the end of all of this is the data. All right, so that's the stuff you're actually sending. So this is an expensive header. If you were to send 1 byte of data, it would take you 1, 2, 3, 4, 5, 6 times 32, right, about 200 bytes, 200 bits worth of information just to get down to your data. So this is where things like buffering become important. If you're going to send something, you usually bundle it up until you've got a bunch of stuff, and then you make one header and push out, you know, a few thousand bytes of data. So here's my favorite ASCII art, right? So this is a picture of how connections are established, how they live, and how they get broken down, right? So you listen for a connection up here, and you get a receive sync, and you send an ACK, and so on and so forth. Your connection gets established, and when it closes, you go into a close wait, and so on, right? Gorgeous ASCII art. So everything you want to know about doing TCP is in this document, basically. We never deal with this, though, right? We're not going to have to know any of this to do what we're going to do in Java. But if you want to know what's going on, or if you don't have Java, if you want to make your own communication system built on top of this network, right, you got to go to a source like this and sort of figure out what the ones and zeros are. And this will tell you everything there is to know about TCP, basically, but probably not in the most succinct way. So 85 pages. So that piece of data that gets sent at the end of the TCP header is an Internet protocol packet, an IP package. So this is RFC 791, and same drill. And there's what an IP header looks like. So the IP header includes the source address and the destination address, 32 bits, right? That's the 4-part IP address, and some information for what protocol we're using, and so on and so forth. So those are worth looking at sometime when you've got some downtime and you're kind of like, I really wonder how this stuff works. Take a look at RFC 791 and 793. They're an interesting read, and it's kind of Minecrafty, right? It's going back to, if all you have is these small set of building blocks, how do I make my world, right? And that's really what you're doing here. You're starting with, I can toggle a 1 and a 0, right? How do we get to the world that we're in today? And you just sort of build up. All right, but we get to skip over most of that because in Java we're just going to deal with sockets. And there's two kinds of sockets that are sort of similar but yet fundamentally different in Java. There's a plain old socket and there's a server socket. And the way this works, the server socket is a socket that you can create and assign a port number to, and something else can request to connect to that socket. Okay, plain old socket you can't request connections to, but a server socket you can. And so typically what you have is you have a server program that runs first, sometimes at boot time, and creates a server socket with a certain port number. And then somebody who wants to use your service makes a connection request, which means you got to know what port number to connect to. So for our chat program, you're going to pick a port number. I'm going to tell you a port number, and you're going to set that up as your socket's port address, and then anybody who wants to chat with you can connect to that port number. But really, these things can be pretty much anything. I don't know if port 0 is actually allowable, but the first 1,000 or so port numbers are reserved. You have to have root access to bind a socket to any of those numbers, because those are the ones that have preset, well-defined meaning, and then starting at 1024, it's kind of whatever you want. And some of the higher ones are also predefined, like 8080 is the secure HTTP connection. But the lower ones are all very particular. So if you look on a Unix machine under etc/services, you'll find a list of TCP socket numbers. So 7 is an echo, right, which should just ping back whatever you send it. 15 is a netstat, which you can use to find out information about the network status. 21 is an old protocol called FTP, File Transfer Protocol. That was an insecure file transfer system. You could make a connection to port 21 on any machine, and if it was running an FTP daemon, you could say, you know, send me this file, or here's a file, please put it in such and such an area. And they let you do transfer back and forth. It's not secure, because you have to authenticate through a password, and the passwords just go over in plain text. And you have no way of knowing how those passwords are being sent at the physical layer, right? So unless you encrypt things, your stuff is just going over in plain text. So I was playing with some Ethernet hardware back in the 80s, and just kind of wanted to see what sort of stuff was going through the network, so I just kind of like put it in what's called Promiscuous Mode. It basically accepts packets regardless of the address, and started looking at those and stumbled across my office mate's password like within 2 minutes. And I was like, can you change your password, because I think I just saw it. So 22 is the secure shell protocol. That's the one that we use when we putty into the Linux server, for example. That's an encrypted version of 23, which was Telnet. Telnet was just totally plain, I'm typing, it's getting sent over, right? And same thing, if you're doing a login session, you type your password, it just sends its characters over. And that was what I accidentally snooped on my office mate. 25, simple mail transport protocol. That's the mail client, mail server. So if you want to send mail to someone on a machine, you can connect to port 25 on that machine and start a little dialogue. You say, hello, introduce yourself, you've got a message from this person, recipient goes to that person, here's the body of the message, and bingo, mail gets sent. Right? A lot of this stuff does not work now because, you know, if you open up a port like this, you're just going to get hammered by all kinds of connection requests. But at one time, this was all freely accessible. So 79 was finger. That's a glorified version of who that lets you see when the person last logged in, how long they've been idle, things like that. You can do that across machines. 80, innocent looking right there, HTTP, that's the web server. So if you connect to port 80 on a machine, you can start a conversation which says, you know, I would like to see the web page called such and such. And it'll go into the area where web pages are stored and find that file, open it up, read the contents, send it to you. That's how your web browser works. And we usually use 8080 or something else which is secure. So all of these things have different different purposes and applications. And so we're going to make sockets and we're going to use them as we see fit. And we're going to pick our own port numbers and so on. All right, so let's get into some code. So let's look at server sockets.
What are regular sockets?
Coming next. So regular sockets are just called socket. And we can create a socket and say I'd like to connect this to a server socket. But if we create a plain old socket, we can't put a port number on it. And so other people can't connect to it. So creating a server socket is very straightforward. We just construct it with an argument, which is the port number. Sockets can be created with port numbers, but I don't think they have accept methods. So let's try this. So we'll import our server socket and we'll import a socket while we're at it. And we'll have a public static void main. So we can try to construct a server socket using a port number. First issue is all this stuff can throw exceptions. Oh, I got a bigger issue, which is I imported the wrong thing. Okay, so all this stuff can throw exceptions. So IO exception must be caught or declared to be thrown. So let's do some try-catch blocks. And here I'm going to get really sloppy and I'm just going to put a try block around pretty much everything that we do because so much of it can throw an exception. Okay, so let's try to make a server socket. And if something goes wrong, we'll print an error message. And so first thing I get is permission denied, bind failed. All right, permission denied because I tried to bind to address 10.
Address 10.
Don't think it's used for anything, but since it's smaller than 1024, it's reserved. Okay, so I haven't tried this, but let's let's try it now. So if I run this under sudo, right, which makes me a super user, it works fine. So if you have root access, you can bind to any port that's not in use. Alright, so I just bound to port 22 and that worked fine because I do not have an SSH daemon running. If I try to do this on the Linux server, I'll get an error because there's already something connected to port 22. But let's not be power hungry. So we can use any socket number we want, basically from 1024 through 65,535. So someone give me a socket number to use.
1083.
1083, I like it. Alright, so we can run that without saying sudo and it seems to work fine. Doesn't give us an error. Doesn't do anything noticeable, okay, but it creates a socket with that port number and then the program exits, so it goes away. Alright.
Do you really want to make it like check until it finds one that's open?
You can do that, so, and then you're basically talking about port sniffing, either on your machine or another machine. And yeah, you can just start at 1024 and either succeed in creating the socket or throw an error, and you can make a map of what's in use. And I think if you do that on other people's machines, they get really suspicious. Even though there's nothing inherently, wrong or dangerous about that as far as I can tell. But it's considered port sniffing and gets people upset. Alright, so server sockets also have this method called accept. So accept says listen for a connection to be made on this socket and accept it. So I can say accept and it will return an object of type socket, which will be a socket that I can use to communicate with whoever made this connection request. So let's make a socket. So we create our server socket and let's say sock equals ss.accept. And I'm going to put some print messages in here.
Sock?
Sick.
Sick. And not accept looks for access ports.
Accept will basically say I am open to somebody who wants to connect to this socket. Wait until somebody makes a connection and then come back from accept. Alright, so we're going to create our server socket. Then we're going to wait for a connection, call accept. Once we get our connection, we're going to print out the socket that came back. Alright, so create a server socket, it's waiting for a connection. I gotta write down this port number because I'll forget it. 1083. Where did my window go? Okay, do it again. Alright, so there's a program called Telnet. It used to be a standard on Unix, now you have to install it specially. But Telnet is basically just a way to communicate with a port on a machine. Totally unsecure, but that's okay. So I'm going to Telnet 127.0.0.1. That's the IP address of your local machine. It's a pseudonym for your own host. Whatever your actual IP address might be, you can also get to your machine by saying that address. And I'm going to connect to port 1083, which is what our software over here is waiting for a connection on. So watch over there where it says waiting for a connection. I'll make my Telnet connection, and it says, hey, connection received. And then it printed out this SOC information, and it said the connection came from 127.0.0.1. This was the port number that it came from, and it's connected to the local port 1083. At that point, our server Java code closed the connection. Well, it exited, which closed the connection, which caused Telnet to say connection closed by foreign host, and then Telnet exited. But we made a connection from this bash session to my Java code running over in that bash session, which is encouraging. All right, so once you have a connection, you have a socket that you're talking on, and here's what's basically happening. You've got a server listening at 1083. You've got a client, creates a socket with some port number on it, right? It was, I don't know, 58,000 something. And when I make a connection to this server, connection request, the server creates a new socket and connects my client to that. Which means if my server went back to accepting another connection, it could accept another request, make another connection, and client 2 could communicate with that. And so typically you have multiple clients connecting to one server, which is why it's a server. Okay, so one of the methods we have available from a socket is get input stream. Return an input stream for the socket. And an input stream is one of the things we can use to construct a scanner. So let's play with that. So let's import our scanner class. So I'm going to construct a new scanner off of my socket.getInputStream. And I should have something I can read from. So I'm going to kick out of my try-catch block at this point. And I'm going to start a new one down here. I'm not going to get fancy. I'm just going to keep going. Don't do this at home. I'm just going to put everything in my first try-catch block. Alright, so our usual scanner loop. Well, there's a next line. I'll take the next line, just print it out inside angle brackets, and when next line fails, we'll close the scanner. And let's go ahead and close the socket that we accepted. Alright, so now that's waiting for a connection. Let's go ahead and do our telnet. You can also telnet to localhost at That's another pseudonym for 127.0.0.1, so that gets you to yourself. And we'll go to port 1083, and it says connection received from port 59.690, and my Telnet session is waiting for input. So I can type here in my Telnet window and hit enter, and hey, it shows up in my Java code.
Hey.
In Telnet, it tells you in the beginning here, the escape character is, that means control right bracket. So if I hit control right bracket, it takes me back to my Telnet prompt. And there's various things you can do here, but I'm just going to do quit. Exit Telnet, I'm just going to use a Q, which will close my connection. And when I do that, my server exits, because it got an exception. Or because the next line failed. And so it closed up. All right, makes sense so far? All right. So if you have a router, you can have fun with this. So if you have a laptop or a smartphone or something that you can run PuTTY on, or Telnet, you can connect to this router. So the router name is CSE223, and it has a super secret password, which is password 223. And I'm going to leave this router in the collaboratorium. We're going to leave it unplugged when it's not in use, but if you want to play around with it for making connections, for testing your code, you can plug it in, connect to that. There's your authentication password. And I'm going to do the same over here. I'm going to disconnect from the student network, and in a moment or two I'll get the option to reconnect, and I'll go ahead and connect to CSE223. So see if you can get connected to the router. It's probably booted by now. And let me know if you have a connection. It's difficult to do these days because a lot of the systems don't want to connect to a router that doesn't actually have internet access. So under Windows, it will try pinging probably Microsoft.com, and if it doesn't get there, it'll say, well, there's a router there, but it doesn't go anywhere. I don't really want to connect to it. You can usually coerce it into connecting anyway. Sometimes it'll just say, you know, do you want to connect anyway? Android does the same thing. Unix seems fairly docile about it. So I should be connected now. So ifconfig is another good command to know. Let me do it over here. So ifconfig tells you the status of your network interfaces. That's the IF. So L0 is a local or a loopback interface. This is the wireless one, WLP2S0. And it tells me that it's up, and my internet address is 192.168.2.7. So let me go ahead and run my server code. So is anybody connected to the router? Okay, can you run, if you run PuTTY and you tell it to make a raw connection, put in that as the address, and then put in 1083 in the window next to it where it asks for a port, that should connect you to this Java program. There we go. Someone connected. Who connected? All right. There you go. Life is fleeting. This is true. So we've got a network connection going, right? And it's wireless, which is cool. Now, if I had more code running here, I could type, and whatever I type, you would see over there. But my code isn't doing anything with what I type. There's nothing reading from standard in or sending it. But it's not that hard to imagine how to do that, right? You create another thread, and that thread reads from standard in, right? Open a scanner on system.in, reads from standard in, and every time that it gets something, it writes that out to the socket. And sockets have a get output stream method, and you can use that to construct a print writer. So then I can just do print writer.println, and whatever I type in gets sent out. Cool. Is that exactly what I typed? Wow, that's impressive. So this is basically, you know, how the network works. And it's not a lot of code. So you can do this in lots of different languages. You can do this in C, and it's a fair bit more difficult because C is just lower level. So you have to put in lots of parameters when you create your socket, and you have to tell it what kind of addressing family, and you have to adjust the host order versus network order because of byte packing orders, big endian, little endian issues, and check lots of errors and all kinds of fun stuff that you'll get to do in a system programming course. But in Java, it's fairly painless. All right, so questions on all of this? So what do we want to do from here? So we got server-side receiving working. We'd like to be able to send from the server side as well, which means we want to be able to do multiple threads. And once you have threads, you start thinking about how are they going to communicate. I have a thread that's reading from the socket and displaying. I have a thread that's reading from my keyboard and sending. If that second thread exits because I hit a Control D, I need to have some way to shut down that thread that's reading from the socket and sending to my display. So I got to think about how to communicate between these threads. And then we'd like to have multiple connections. Because maybe you want a server that multiple things can connect to. So we'll play around with that, and that's another application of threading. We'd also like to do some I/O that's raw, that's less cooked, because scanners are very high level. And for example, it's hard to read a single character using a scanner. You can say next line and get the whole line and then break it up into characters, but if you really just want to read one character at a time, you can't really do that with a scanner. But we can use data input streams and data output streams, for example. So we'll play around with some different types of streams. And we also want to look at connection info. So for example, when we got the connection, it said the address that it came from was 192.168.2.2. That was his address when he connected to the router, right? So if you look in the socket class, we can do things like get inet address, right? Return the address to which you're connected. When we bind, we can use a socket address, and when we construct, we can use an inet address. And inet addresses come in lots of different flavors. So we can make an inet address as, you know, something dot something dot something dot something. We can make it with the name of a host, like google.com, right? And all of this stuff is bundled up in objects and methods of objects, right? So there's ways that we can get an IP address and turn it into a host name, or take a host name and turn it into an IP address, and so on and so forth. So we want to play with some of that stuff. So host names, etc. And then somewhere along here, Friday, we're going to talk about PA5, which will be using some of this. And then somewhere after this, I want to go on and talk about web stuff, because there are classes like the class URL that are designed not just to do low-level socket communication, but to really support that application layer. So we can do things like, you know, open a connection to this server and get a web page with this name. And we can do that in a few lines of Java. So we can make a web browser really easily, or we can pull down various resources in different formats. So we'll play around with that stuff, and some composite of this will probably take us through the end of next week. Right, so tomorrow's Open Lab. Friday will mostly be PA5, but we'll continue on this track. We'll get into there further next week. And then week 10 is going to be project presentations, wrap up, discussion of the final, and we're kind of done. So we're coming to the end really fast. But we've gotten through a lot of stuff. So this has been a good pacing of things. All right, that's all I got. So hope you can enjoy the weather, and I will see you tomorrow and/or Friday.